moving on to part 2 of the Lorentz transformation. We brought back one of our props here, taped it up on the board. We'll see what we're going to do with that in a minute. But in this part, we want to focus on the time equation, the time transformation equation. In the last video clip, we were focusing on the x location, the x transformation equation. So we have T rest equals gamma, remember rest frame and moving frame here. And we're measuring Alice is in the rest frame, Bob is in the moving frame, moving to the right at velocity v in the positive x direction. So gamma times a time value in the moving frame plus gamma v over c squared times an x value in the moving frame. In other words, x and t, the moving frame values, are measurements made by Bob. We want to transform that into a time value for Alice in this case. So just as we did with the last equation, let's explore this a little bit. Let's just say, let's just let x moving here, in other words, Bob's measurement of some event in the moving frame, let that equal 0. Okay, very simple. And then, of course, this term becomes 0, and we're left with t in the rest frame equals gamma times t in the moving frame, which should remind ourselves of the time dilation equation, because that's exactly what it is. Does this make sense? Well, remember, when we derived the time dilation equation, we used the light clock. And the light clock in the frame here, in Bob's frame, okay, is just, beam of light bouncing up and down like that in Bob's frame. He's carrying along with him. And Alice, of course, sees it at a diagonal, and that's where we get the time dilation effect. But as far as Bob is concerned, if he's carrying the light clock with him as it goes along, that bouncing up and down is happening in his moving frame, what we're labeling the moving frame from Alice's perspective, but in Bob's frame at x equals 0, okay, because it's in his cockpit with him, and that's his definition of the origin, right? As far as he's concerned, he's not moving. And so essentially, for that light clock example, we had the x value for Bob in the moving frame be equal to 0, and we see it falls right out of the Lorentz transformation equation as it should. We just get t in the rest frame, time measured in the rest frame is gamma times the time measured in the moving frame. Gamma is greater than 1, greater than or equal to 1, of course. And so the way we wrote it previously was something like this. We said time in the moving frame equals 1 over gamma times time in the rest frame. Obviously, you can write it either way there, but this emphasized for us at least the time dilation effect, gamma being greater than or equal to 1. So the elapsed time in the moving frame is slower than in the rest frame. Moving clocks run slow was how we termed that. So Lorentz transformation equation for that checks out. It gives us our basic time dilation result that we derived earlier. Now, though, let's say, what if we just let x moving be anything here? So this is where we come back to Alice here. So we can't simplify our equation at all. We're assuming that v is some value. I guess we could say certainly if v is 0 here, as we did before, then gamma's 1, and you just get time in the rest frame equals time in the moving frame. In other words, both Alice and Bob are sitting there with their clocks. They're not moving with respect to each other, and they measure the same time. So that's a trivial case there. But what about the general case where Bob is measuring some time in his moving frame, and of course, he's not considering himself to be moving. This is from Alice's perspective in his frame, and an x value in the frame. Well, let's imagine the situation that Alice is here. We'll put her in a spaceship, but we'll assume she's at rest. Let's bring back Bob in his spaceship, each with their lattice of clocks, each of them synchronized in their own frame of reference. And as we've drawn it here, of course, Bob is moving like this. And so let's imagine that right about, let's get this lined up here a little bit, right about here, obviously he probably would have traveled much farther than that, but that Bob observes a certain event. Actually, let's not even do it that way. Let's say that Alice, at an instant in time on her clocks, sets off photographs all along her lattice of clocks. And she photographs not only her clocks, but the corresponding clocks of Bob, wherever he happens to be at that instant in time. Okay, and let's just say it's 10 seconds. Okay, so on Alice's clock. So at 10 seconds, Bob is flying by here when they're right next to each other. Both their times say t equals 0, ta equals 0, tb equals 0. And then later on, at some point, way down the line, of course, but we won't show that. We'll just imagine about right here. 10 seconds have gone by. Alice takes photographs at all her clocks at that instant in time. The question is, what are the readings on Bob's clocks? And we're not going to put numbers in here. We just want to get a qualitative sense of this at this point. So let's imagine it's something like that there. And note one thing about our equation here is that, let's say we've got a time right here. These are all 10 seconds reading on Alice's clock. So we've got 10 seconds on that one. What is the value of the corresponding clock right here going to be on Bob's clock at that instant in time? Well, according to the Lorentz transformation equation here, if this is 10 seconds over here, according to Alice, I've got something plus something over here. And assuming both those terms are both positive terms here, we're assuming nothing is 0, because v is not 0, gamma is not 0, obviously. X is not 0. In other words, the x value is maybe 1, 2, the third clock out there, the second clock, or something like that. So what that essentially means is if this is 10, then this term here has to be less than 10. And in particular, t moving has to be less than 10. In other words, the time on Bob's clock, whichever one you point to out there, has to be less than 10. And that, again, is an indication of the time dilation effect, that the moving clocks are going to run slow. They're perfectly, at least the clocks right here at t equals 0 said, fine, everything was set up, not all the clocks, but just the clocks at t equals 0. But down here, as it went on, we find when Alice took the photo that the time on, say, I guess I've been pointing the second one there, whichever one I've been pointing to, time has to be less than 10 because gamma is greater than 1. This term also is positive, and therefore the value of time on Bob's clock in the moving frame has to be less than 10. Okay, so that's sort of an interesting result. It just reminds us of time dilation. But now let's also think about something else, because remember, Alice took pictures along the whole line here of her clocks. And so 10 seconds on this clock, and we can read off the value on Bob's clock at that instant in time. And then what about the next clock over? Also 10 seconds for Alice. So again, this is 10. But note what happens as we move over one clock. The x value here in Bob's frame also gets larger by whatever amount it is. We could use our other equation to get that. We're interested more in the qualitative argument here. So as we move this way, so 10 seconds on this clock, some value on Bob's clock that's less than 10. As we move this way, let's just say it's 8. Give us a number here. So say it was 8 seconds on Bob's clock for that one. As we move this way, this value is getting bigger as we move from that clock to that clock. Therefore, for the next clock over, this has to be even less. If this was 8 for this clock, then when we move it one over, this term is getting a little bit bigger. This term has to get a little smaller. So this has to be a little smaller than 8 now. And if we move over one more, still 10 seconds on Alice's clock, so this is still 10, but this term's getting a little bit bigger even, and therefore this has to get a little smaller. So as you move in this direction, again, all Alice's clocks are 10 seconds, but Bob's clocks, the time as Alice observes them through her photos here that she's taken, the time on these things is getting smaller. It's really prior in time. Again, if this was 8 seconds, this maybe has to be 7.6, and then the next one over is 7.2 or something like that as it goes on. And what that means is this is another verification of something we've talked about before, and that is leading clocks lag. Okay? In other words, leading clocks lag is built in to the Lorentz transformation equation through this term right here. Because otherwise, put this down for a minute, otherwise this sort of looks strange because the Galilean transformation, we just had, TA equals TB, T rest equals T moving. There was no change. And so we'd expect, okay, special theory of relativity, gamma is going to be involved. So we might expect something like T rest equals gamma T sub moving without this term here. And we can sort of get a handle on that. But then this term is just weird. We say, how does that work in terms of not only an effect on time here, but you're adding some distance in here, as it were, in a sense, a distance factor that's affecting the time observed in Alice's frame of reference compared to Bob's frame of reference. And what this term essentially is doing, that another way to put it, is leading clock's lag. As we were just trying to argue here, is that, again, Alice takes all the photographs at t equals 10 seconds. So all her clocks say 10, but maybe Bob's clock here, because I've got two terms here, they're both positive. If this is 10, that has to be less than 10. We said maybe it's 8. But then as you move over 1, this is getting bigger. You're moving in more positive x direction there. And therefore, if this is 8, that's got to be 7.6 or something like that. Move over again, got to be down to 7.2 now, because this term keeps getting bigger. This term has to keep getting smaller. Again, we don't see these effects, at least not in everyday life, because look at the factor here, not only gamma, of course, but v over c squared. This is a very, very small number. So it does show that leading clocks lag, and in fact, in a later video clip, we're going to look at that in a more quantitative fashion to figure out exactly how much do leading clocks lag by. But this isn't showing, therefore, that the time equation, as part of the Lorentz transformation equations, has this built-in, not only the time dilation effect, which we got from our light clock, but also the leading clock's lag effect as well. So that's part 2 of exploring the Lorentz transformation. In part 3, we're going to look at the case where, what about from Bob's perspective, looking at Alice, or in general, what if we have some frame of reference moving to the left instead of to the right?